Hi, my name is George Elliott, and today I'm going to talk to you about something that you're all probably familiar with, gases. And perhaps you can remember going back to elementary school, learning about the three states of matter: solids, liquids, and gases. But what you probably don't know is that all these states involve the differing phases of molecules. As a chemist, it's my job to understand and learn about the interactions and reactions that molecules have with each other and other molecules to help describe the natural phenomena that we observe on a daily basis. So, I'd like to take you on a little bit of an in-depth analysis into the behavior of gases and the work that went into kind of developing an understanding of how they work. And I'll do that by first describing, what is a gas and what are its basic properties, 2, the ideal gas equation and the laws that went into help developing it, and finally 3, real gas laws and the correction it offers to the ideal gas law. So first, what is a gas? It's one of the 4 states of matter. Yes, there are 4, fourth being plasmas. Most people don't learn about those, but that's alright. We're focused on gases today. And gases tend to act as a free particle, almost a free particle, occupying the entirety of the space in which it's contained. And they have 3 basic properties, being pressure, volume, and temperature. Pressure is just the result of collisions at the molecular level with both other molecules and the walls of the container that holds it. Volume is simply the space in which something occupies, in this case being the gas. And then temperature, perhaps the more confusing of the 3, is actually directly connected to the kinetic energy of molecules. The faster a molecule moves, the hotter it is. The slower it moves, the colder it is. Now that we understand those 3 basic properties, we can start describing their relationships to one another and eventually understand the ideal gas law. So first, Charles' law. Charles discovered that when pressure was held constant, as volume increased, temperature increased. Then there's Lusac's law. When volume is held constant, as pressure increases, so does temperature. And finally, there's Boyle's law. As volume decreases, pressure increases. And now when we take those 3 laws and sort of combine them, we get the ideal gas law. PV equals nRT, where N is the number of moles of gas that we have, the amount, R is the universal gas constant, P is the pressure, V is the volume, T is the temperature. But what's wrong with this ideal gas law? Well, first off, it considers collisions to be elastic, which just means that there's no transfer of energy when a collision occurs. But we know this isn't true. If we were to bounce a tennis ball, it wouldn't just continuously hop the same height. It would have a big hop, smaller hop, smaller hop. That's because energy is transferred from the ball to the ground. That's natural. Also, we don't account for intermolecular forces present. Naturally, molecules attract and repel each other. We need a way to account for this. And also, we need a volume correction. If we go back to the equation for the ideal gas law, PV equals nRT, we notice that if temperature equals 0, therefore also so does volume. That can't be true, so we need a correction. So, in that sense, real gas laws needed some sort of description. So people started experimenting, started writing mathematical formulas, and volume correction, that was fairly simple, but we needed a way to account for those intermolecular forces. And early work was done simply just by trying to fit the bill. It took a lot of experimental points and trying to find some equation that developed a curve that could sort of fit all that data. But the best of work was done by a scientist from the Netherlands known as van der Waals. Johannes Diederik van der Waals, born in the Netherlands, grew up relatively poor. He was barred from ever entering college as a serious candidate for diploma. He eventually became the apprentice of a school teacher and eventually later became a school teacher and wasn't allowed to really go for that PhD until later in life when he finally wrote his thesis entitled on the continuity of gas in the liquid state, in which he described an equation that provided us a true real gas law. Van der Waals' equation of state. In his equation, he provided his correction for the volume and a correction for attractive forces using constants that we now know as van der Waals constants. And if you were to open any Gen Chem textbook, you would find a list of values for these constants for specific gases, which we still use today. So what have we learned today? We've learned about what a gas is and its basic properties, pressure, volume, and temperature. We've learned about the ideal gas law and the laws that help describe it, and we've also learned about real gas laws and the work of van der Waals himself. So, that brings us to an end. And of course, I'd like to first thank William N. Davis and his work and his textbook that has truly been an inspiration to me and truly helped me put together this presentation. He's been one of the greatest professors I've ever had, and he's truly taught me that imagination is key to helping understand the physics behind chemistry. And I'd like to leave you with a last-minute quote that I feel truly resonates with the lessons we've learned today by my favorite scientist, Albert Einstein. Logic will get you from A to Z, imagination will get you everywhere. Thank you.